Hey, how's it going? All right, let's do a sound check. Can people hear me out there?
Yes.
Can you speak up again?
Yes.
Good, thank you. Review, or review today, and also Monday. Okay. Okay. All right, let's begin. So I think I've sort of said this like many times, so I won't write it down this time, but I think I'll probably send a message out to you later. So the midterm, so our next week, week from today, the first group, the Bulldogs will be there, should come. And then the second day will be Friday, a week from this Friday. And then the Georgia should come, okay? Yeah, and this Friday we have no classes because we have fall break. All right, is that clear? Okay, good. Okay, so today we're going to review. So this is a review part 1 for midterm 2. All right. All right, so the first thing I want to do is I want to give you a list of terms that we've used. And I highly suggest that you write down the definitions. Let's see, you could just put them on flashcards and make sure you have them down by heart, okay? So here are the definitions I'd like you're accountable for. So one is, what does it mean for vectors to be linearly independent? So some of this is an overlap with what you had on the first midterm. Span, okay. Basis for, let's say, a subspace, okay. You should know what a subspace is. Okay. Let's see. The inverse, actually, you should know what a linear transformation is. You should know what it means to be one-to-one, what it means to be onto. Let's see, what else? Okay. So you should know what an inverse of a matrix is. And then we have the null space, the column space. These are things we will review. The rank of a matrix and the dimension of a subspace. And the last definition is the definition of a determinant. There are many definitions, but you should at least know one. Okay, any questions on this list? Yeah, I really advise, in math, there are not like so many definitions. It's not like biology. So, I would take the time in your study to actually put these things on flashcards, maybe. So here's just a word of advice. Maybe sort of make some flashcards for these.
Dr. Collins,
Yes.
when you say know these definitions, do you mean like be able to just repeat the actual definition or
Yeah.
how to apply it?
Yeah. So all I'm saying is that I could just say to you, say what it means for a function to be one-to-one.
Okay.
Say what it means for a set to be a basis.
Okay.
Let A be an m by n matrix. Define the null space. That kind of thing, right? So these are just they're almost like gimme points, right? If I ask you a question, you just have to repeat, like what the definition is.
I had a quick
Okay.
question.
Other questions?
Yeah, I had a quick question.
Sure.
So for the inverse of a matrix, I guess would that mean you want us to memorize like the IBT?
Just say an inverse. So A is an m by n matrix, and the inverse of A is a matrix B such that AB is equal to identity and BA is equal to identity.
Okay.
Okay?
Mm-hmm.
Yeah. Okay. In math, terminology is quite important. So this is why, I do have you actually know, various definitions. Especially the basic ones. I don't really care if you know what, defining like echelon form is and reduced echelon form and whatever echelon form. That's not important. These are very important definitions to know, like for any class that follows this, or even some of your more applied classes. Okay. All right. So this lecture is not going to be linear. even though it's linear algebra. So what I'll do is I'm going to talk about topics, like for example, Gaussian elimination, and I'll put it into context in terms of how we actually use Gaussian elimination. All right, so the first thing I want to talk about are systems of equations. And Gaussian elimination, okay? All right, so, the story starts out like usual. A is a m by n matrix. Okay. And the first thing we ever learned was we looked at a system of equations like ax equals b. So this was a system of equations. Now, we have a method and a machine for solving any system of equation that I give you, okay? So we have this process called Gaussian elimination. And so what do you do? Well, you sort of form this matrix with A on one side and B on the other with a line going down there. And you do row operations to transform A into something in echelon form. So we use the Gaussian elimination and we get something like U here and maybe some B prime. Okay, and U is in upper echelon form. Okay, so it's so U looks something like this, where you have a certain like staircase looking thing, and then you have sort of non-zero entries on the rows, and the first non-zero entry on the row is a pivot. Okay, and these invariants are quite important because it tells us like how big the solution set's going to be for the system of equations. Okay. All right, so this is the bread and butter. This is what we use all the time. So here is a checklist to make sure that you know how to do these problems using Gaussian elimination. All right, so know how to, I'll make a little list. So first, you should be able to solve systems of equations. Okay, so if you have ax equals b up there, you should be able to just solve for x. And your x could be unique, or it could be, there could be no x, for example, it could be inconsistent, or it could have, like infinitely many solutions. Right? And you ought to be able to sort of determine like what happens in any given case. All right. The second thing you should be able to do, which is sort of related to this, is you should be able to find the null space of A, which is the solution set for AX equals 0, and the column space of A. Okay, we'll just do this. What am I doing here? Okay, and the column space of A. Okay, so you should actually be able to find bases for the null space and the column space. Okay, we actually did this beforehand. Maybe we'll review it, I think, this in a moment, okay? Yeah, we'll do that in a second. Okay, you should also be able to check when vectors are linearly independent. Okay, so in order to do that, you have to look at the system AX equals 0, where the vectors are in the columns of A, right? So I'll just go over this real quick. So we've done this many times. And then what you do is, so you put the columns, you put the vectors in the columns of A, you check whether the homogeneous system has the trivial solution or could have infinitely many solutions. If it has infinitely many solutions, what can you say about the vectors?
Linearly dependent.
They're linearly dependent. Good. Okay. Good. Okay, so that's old hat for you guys. So you should also be able to check whether a vector B is in the span of these vectors, V1 up to VT, let's say. Okay? So then that comes down to a system of equations thing too, where you're looking at AX equals B. Okay? So if the system is consistent, the answer is yes. If it's inconsistent, the answer is no. Okay? And then from this, in general, you should be able to determine whether the vectors span a certain subspace. I didn't say that quite right. Let me do this over again. So I gotta take a mulligan on this one. Okay, so let me do this again here. Okay, so I want to check if the span of these vectors V1, V2 up to VT is equal to W. Okay. So to check whether the span is equal to double, you have to check that for every vector in W, your system is consistent. Okay. All right, so what else did we do? We did the LDU decomposition. Okay, so we're able to factor a matrix in terms of a lower triangular or diagonal and an upper sort of triangular or upper echelon form. Now, we can do this as long as we don't need row exchanges. So up to row exchanges, we have a LDU decomposition. All right, what else? You can actually compute inverses. All right, so if I want to find an inverse, what do? Well, I do A and I over here, and then I use Gaussian elimination, and I convert the left side to I, and the right side becomes A inverse. Okay? And then we actually were able to compute determinants using Gaussian elimination too. All right. Any questions on this? Yes, no? Okay, good. All right, so let me review a couple topics for you. So one topic is the idea of linear independence. All right, so let me first review the definition. So a set of vectors V1, V2, VT, and let's say Rn is linearly independent if and only if when we have C1 plus C2 plus CT VT, that's equal to 0. This implies C1 is 0, C2 is 0, and CT is equal to 0. Okay. All right. So so again, to show linear independence, we could actually look at the solution sets of AC equals 0. Okay. So if this has only trivial solution, this implies it's linearly independent. And if it has, let's say, infinitely many solutions, then it's linearly dependent, which means not linearly independent. Okay? All right, so that's linear independence. And then, again, the span. So again, let me just remind you of how we did this. So B is in the span of vectors V1 up to Vt. If and only if B, okay, so who can fill in the blank? So something is in the span if and only if what?
If B is a linear combination of the vectors, V1 through Vt.
Yes, CV1 plus CV2 plus CTVT. Very good. Okay. So if and only if B is a linear combination of the vectors V1 up to Vt for some C1, C2 up to Ct. Okay. All right, 4. Okay, I'm gonna sort of do this slightly out of order, so I'll go through subspaces later. Okay, so this is the notion of a basis. So I'll let W be a subspace of Rn. Okay, so the set V1 up to Vt is a basis for W, if and only if. Okay, so what conditions have to hold?
The zero, they're linearly independent. The vectors are linearly independent.
Okay, just hold on for a second. Good, that's the first one. V1 up to Vt are linearly independent. Okay, then what else do we need?
That W is in the span of the vectors,
Is W in the span or equal to the span?
equal to the span.
Okay, good. So W is actually equal to the span of V1, V2, up to Vt. Okay, so every vector in W has to be a linear combination of these vectors. Right? Okay, so you know the general picture looks something like this. Let's say W is this plane. The idea is you have two vectors here where they're linearly independent, and any vector in there in the plane can be written as a linear combination of these two vectors. Okay, questions on this? Okay, let me give a practice problem. So here's an exercise, is to determine if these vectors 0, 1, 5, 1, 2, 8, and 4, minus 1, 0 is a basis for R3. Okay. All right, so I think I've given you the tools to do this, and you should go through this and make sure you know how to justify it. Okay, any questions on this? All right, so let's look at the notion of subspaces next. So let's see, we did 4 here, so we're on to number 5. All right, so let's go over the notion of a subspace. So let's make a definition. So W contained in Rn is a subspace on if and only if two things happen. The first, it just has to be closed under vector addition, right? So if W1 and W2 are in W, then, let's put a little if here, then W1 plus W2 is in W. Okay. And it has to be closed under scalar multiplication. So if lambda is in, let's say, R, W is in W, then lambda times W is in W. Okay, so remember, we can also put axiom number 3, which actually follows from 1 and 2, that the zero vector is also always in a subspace. Okay. Questions on this definition? So, subspaces are going to look, linear. They're either going to look like lines and planes. They're going to look flat, okay? And they have to go through the origin. So that's kind of the picture you should have. Okay, so the dimension of a subspace equals the number of elements in a basis for, for W. Ooh, I don't know where I got the 8 from. Thinking too far ahead. For W. Okay, so in order to find the dimension of a subspace, you should just try to find a basis for the subspace and just count the number of vectors in there. All right. So now I want to talk about two specific subspaces. So these are specific examples. All right, so the first example is the null space. So we're going to start with A being an m by n matrix. Okay, so first one is let's look at the null space first. So the null space is just going to be the set of solutions of the homogeneous equations, right? So this is going to be the set of all x such that ax is equal to 0. Okay, so we actually proved that this is a subspace. Now, how do we actually find a basis? So what we do is we look at A0 and we transform it into U0, right, using Gaussian elimination. And then we actually solve. Okay. And we have that, let's say x1 up to xn is equal to, let's say the free variables are s1 v1 plus s2 v2 plus st vt. Okay, so the s1, s2 up to st are the free variables. Okay, so we've done this like a jillion times. I mean, we actually have solved this. We've actually found the solution. And then to get a basis, you just take the vectors next to the free variables. So first of all, the dimension of the null space. So what's the dimension going to be?
Number of free variables.
Which is in this case?
T.
T. Okay. And a basis for the null space is V1, V2, up to VT. Are the vectors that you just get in the solution set to describe the solution set. Okay, any questions on this? All right. 2. So we have the column space of A. All right. So how do we find a basis for the column space? Well, we use Gaussian elimination again. So you could just take your matrix here, A, and then you sort of use Gaussian elimination, and you get something in sort of upper echelon form. And this is U, all right? And you just don't take the columns in U, where the pivots are. So let's say the pivots are here, 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 and here. So in order to find a basis, so first of all, let's look at the dimension. So the dimension of the column space of A equals the number of pivots. Okay? And so you just don't take the columns in U corresponding to pivots. You have to go back to the columns of A that correspond to the non-zero pivots. So let V1, V2, let's say to VS be the columns of A corresponding to the pivots in U. Okay, so then this set is a basis for the column space. Okay. Any questions on this?
I have a quick question.
Go ahead.
So the column space compared to the span, I suppose, of A itself is the column space just takes out the redundant vectors.
Yes.
Okay.
So the vectors in the columns of A need not be linearly independent. So what you're doing in this process is actually picking out a linearly independent set.
Right.
That still spans, that gives you the span of the columns of A still.
Okay. Gotcha. Thank
Okay.
you.
All right, so why don't I give you a practice problem here? Here's another practice problem. Yeah, I don't know, maybe, okay, I'll just kind of make it up. All right, so it'll work still. So, I mean, it may not be as rigged as maybe one would like, but that's okay. So this is 4, 1, 0. Let's put extra ones on here like this. Okay, so the problem is to determine the dimensions of the null space of A and column space of A, and then find a basis for the null space of A and a basis for the column space of A. Okay, so I give you this nice 3x4 matrix, and you should be able to do this using the techniques that I mentioned above. All right, now the rank is just a dimension of the column space. So note the rank of A equals the dimension of the column space, which, as I mentioned before, is just the number of pivots. All right, let me take a brief pause. Any questions?
Yeah, I have one. So
Yeah.
maybe I kind of like misunderstood column space of A, but I have in my notes that the column space of A is the span of the vectors.
In the
And did-
columns.
Okay. Could you just scroll back up to that part? I think I maybe misunderstood something. Okay, thank you.
So see, the point is the columns of A need not be linearly independent. So what we're doing is in this process, we're picking out various columns so that we do get a basis. So they still span and they're linearly independent. Question? Yeah, go ahead.
So is the only difference between the null space and column space as far as is the dimensions of each? Because for column space, it's the number of pivots.
No. Well, I mean, the thing is, it's the sum of those things is going to be equal to the number of columns, right? So if I take the dimension of the row space, sorry, null space and the dimension of the column space, I get the number of columns, right? Now, remember, they live in different spaces, right? The column space lives in RM. Let me make sure this is clear. So remember, the column space lives inside of RM. The null space lives inside of RM. Okay, so they actually live in different spaces, right? But there's some compatibility with dimensions. Okay, all right, good. Other questions?
I just have maybe a quick question.
Sure.
So the column space will always give you an n by n matrix.
The column space. The column space is a set of vector. I mean, it's a subspace. It's not a matrix.
Okay, so the subspace will always
See, the column space is a subspace. You can describe the subspace by describing a basis. And this procedure that I gave you describes how to get a basis for the column space. Okay? Does that make sense?
yes, that makes sense.
Okay. good.
And one more clarification on that. You mentioned the column space can be linearly dependent, right?
No. The column space is a subspace, okay? It's a subspace. The columns of A, the span of the columns of A, give you the column space. So let me just write this down, all right? So the columns of A, column space is equal to the span of, let's say, V1 up to VT, where A is going to be equal to V1 all the way up to VT. Let me call this W1 up to WT, just to make sure I don't mix it up with what I did before. Okay? So remember, the column space is the span of the columns. And so if you want to find a basis, you want to know which vectors to throw out, because the vectors can sort of be redundant. So you want to be able to have a procedure for doing that. And so this procedure I described above actually gives you a way to do this. So you use Gaussian elimination, you get to the U part, and then you find out where the pivots are, and then you go back to A and you take the columns corresponding to the columns that the pivots occurring. And that'll give you a basis. Okay? All right, so let's continue on. Okay, so there are a few topics I just want to cover briefly before I can open up to some questions. I'm going to handle LDU decomposition determinants on Monday. Okay, so the first thing, the one topic that I want to cover was just a little bit about linear transformations. So that's I don't know, number 6. Okay. Okay, so let's do that. Okay, hold on here. Okay, number 6. Okay, linear transformations. All right, so let me give you a definition. So linear transformation T from Rm to Rn is a function such that, well, you can almost guess again, right? You just want to make sure vector addition and scalar multiplication are preserved. So T of V1 plus V2 is equal to T of V1 plus T of V2. So V1 and V2 are in Rm. And 2, T of lambda V is just lambda T on V, where lambda is scalar and V is inside of Rm. Okay. All right. So now let me just relate to you the concept of one-to-one and onto. So first of all, we know that T x can be written in terms of A times x, where A is just T of E1 down the column and T of E, let's see. So let's see, how many basis vectors do we have? Rm. Let's see, is that right? No, it's T of Rn going to T of Rm, sorry. Okay, so T of En, that's right. Okay, so what you do is you take the unit vectors and you apply T to them, and then you could represent your linear transformation this way. Okay, so once you do that, it's not hard to prove one-to-one and onto. So T is one-to-one if and only if Ax equals 0 has only the trivial solution. And then 2, T is onto if and only if Ax equals B has a solution for all B in Rm. Okay. All right, so we've actually done this, and so I'm just saying what you should kind of know from the first midterm. So you should know how to prove T is one-to-one and onto. Okay. All right. Now, this one again, the midterm is cumulative, but it's going to emphasize more of the second half after the midterm. But I still expect you to know certain things about how to balance chemical equations. So you should still know how to. So other applications that you should review is like balancing chemical equations, maybe some things involving networks. One of the example that I had in class, and sort of economic models. All right, so that sort of covers the first part. Now, I just want to be brief in the remaining time, and hopefully I'll have a little bit of time to answer general questions. Okay, so So last thing I want to touch upon today are matrix operations. Okay, so of course you should know how to add matrices. You should be able to multiply matrices by scalars. You should be able to multiply matrices too. Okay, so these are all things that you're doing right now. And you should also know what a transpose of a matrix is. So if A is equal to Aij, then the transpose is obtained by sort of flipping the rows and columns. It's just Aji. Okay, so if it's a square matrix, all you're doing is you're just flipping the entries along across the diagonal. Okay, so I think that's enough review material for the day. So let me just mention, so the next time we'll cover LDU decomposition, and we'll cover determinants. Okay, and then including inverses. Okay, so that'll be the topic for Monday. Okay, so we have a little bit of time left. So are there any questions on this material that I presented today?
I had a question.
Okay.
So just clarifying this, the material that's going to be covered on the midterm, the cutoff for that is 3.3.
That's correct. So up until, yes. Absolutely. Let me see. Let me just make absolutely sure here. Yeah. So it's 3.3. Okay. Through volumes.
Which is our homework this week too, right?
Right. So I'll try to, I know I'll try to mention it to the grader. But luckily you have a copy still in Notebook, right? So you can still use it to study from. Okay, other questions? I'll keep that in mind too when I make the midterm up, Okay, other questions? Yes, no? Okay, so hopefully we can have a little bit of time after the next review session also if you have questions on determinants, inverses, LDU decomposition. Okay, great. All right, so everyone have a safe and happy fall break, and we look forward to seeing you back again on Monday. Okay.
Thank you.
Okay. Have a good one. All right.